Okay, let's begin. Let's begin. I know. At least it's not 7, because there are 7 o'clock classes. Okay. Let's see. Class notebook. And we are on section 01. Okay. Okay, so we stopped here. Last class, we were talking about material classification into 3 groups: conductors, insulators, and semiconductors based on the material property of resistivity. Homework 3 was assigned, and I posted an announcement. Typically, um, I will always use announcements as a way of communicating with all the students. So please ensure that you're keeping up with your with the announcements, and also enable the notification settings in Canvas. Okay, so there are settings you can turn on and off. If the setting is off, it will not send you a notification every time an announcement is posted. Sometimes if it's critical, I might use the email, but more often than not, I will just post an announcement. So in the announcement was homework 3, and homework 3, there are a couple of problems. Sorry, actually, there's a couple of multiple choice questions, and then one is a problem based on this equation right here. Resistance is equal to rho L over A. So you simply take the information that's given to you, extract the relevant numbers, and plug into this equation to calculate the resistance. Yes. Uh-huh. So it'll generally be ohm centimeter. Ohm centimeter, yes. So the question being asked is, what units should we use in the yeah. Well, when you perform the calculations, everything should be converted. Meaning, if it states microns, then it's 10⁻⁻6 meters. So then we use the unit prefix when we do our calculations. Okay, but I believe the answer is the units are already given, I believe. Yeah, so if it's just ohms per meter, then you have to enter it as ohms per meter. If the answer is asked ohms per centimeter, then, sorry, not ohms per cent, ohm centimeter, then you enter units for ohm centimeter. So resistance in ohms, and when you're calculating in general, you have to take the unit prefix into account. Yeah, I get your question now. Okay, when it asks just for resistance in ohms, or length in meters, or whatever in microns, when you perform your calculations, you must always take the unit prefix into account. So in your calculations, if it's centimeters is 10⁻², then you have to use the unit prefix, the exponent. Otherwise, your answers would be incorrect, right? All right, and then we go here where we were talking about the most common semiconductor materials: silicon and germanium, intrinsic semiconductors, meaning inherently they are semiconductors. Okay, and then we have compound semiconductors. So silicon and germanium are intrinsic semiconductors. And germanium was actually the first semiconductor used to develop a solid state device, which was the point contact transistor. And then silicon, of course, because of its superior properties and ease of manufacturing versus germanium, quickly took over as the de facto material of choice. Then we have compound semiconductors. And compound semiconductors made up of two or more elements. Okay, 2 or more elements. So again, it's a compound semiconductor when you take 2 or more elements and create a new material that can behave as a semiconductor. That's a compound semiconductor. In general terms, compound semiconductors are now used for just two two material semiconductors. If it's made up of three, actually this will be a classification under compound semiconductors, then it's known as ternary. It's made up of four, it would be quaternary. Okay, ternary and quaternary. So put this on the side. Okay. Intrinsic semiconductors are also known as elemental semiconductors. They are from column 4 of the periodic table, so they have 4 electrons in their outermost orbit. Okay, so right here, elemental semiconductors. And so almost everything that we learn in this class is based on silicon. Okay, diodes, Zener diodes, transistors, FETs, MOSFETs, everything is based on silicon. That's the most prevalent material for semiconductors in today's world. Some examples of ternary compound semiconductors are gallium arsenide, gallium nitride, there is indium phosphide, then for ternary, there is, let's see, compound semiconductors. So I skipped over that point. Compound semiconductors are made up of elements from column 3 and 5. So you combine columns 3 and 5. Again, you get 8 electrons in the outermost shell when you combine them. Or it could be 2,6 also. So 2,6 semiconductors, an example would be cadmium and sulfur, cadmium and selenium. It could also be, I believe I've heard of cadmium and tellurium. So, but yes. Two six, yes. Yes, that's correct. Yeah, the first ones are from 3,5 and the last two are from 2,6. So, see. 3 plus 5 here. And then 2 plus 6. Now, obviously, we cannot just go around just combining materials and expect it to behave like a semiconductor. There is a deep science behind everything. Okay, so researchers have tried to do this. They've tried to create new materials, not always successful, right? There's always downsides to it. There's very, very few materials that actually pan out in an actual usable form, and even more importantly, that can be commercialized at a on a monetary scale. We have LEDs, right? LEDs are typically made from gallium arsenide. So the question being asked is, some of these materials are toxic. Yes, that is correct. They are toxic. And but it's very, very small amounts, and they are encapsulated inside, inside packaging. So as an example, as I was saying, gallium arsenide, gallium arsenide, made an error over there, is typically used for LEDs. And depending on the amount of impurities and doping, you can have different colors. But it's encapsulated inside a plastic or epoxy packaging. If you look at an LED, what we see is basically the packaging. You have the red plastic packaging, and if you hold it up to the light, you can see the actual semiconductor is like a tiny dot, very small. Okay, that's how all electronics are. Most of the electronics, the chips, the transistors, discrete components that we use, they're actually very small in size. The packaging is what makes it really big, always. Let's see, what else? Oh, so as I was saying, we can try and combine all of this, but there's a deep science behind every material. What we will learn in this chapter is basically an entire course by itself, EE 524, solid state electronics, where you learn about device physics. I kind of find it fascinating because it's sort of my wheelhouse, but it's not everyone's cup of tea. But again, as an illustration, this one single chapter is an entire course. Let's see. Okay. In the last couple of 100 years, there have been researchers and physicists who have postulated many models of the atomic structure, right? One of the most famous one that had been in use for a long time was developed by Niels Bohr, came to be known as Bohr's model. It was actually a modification of the Rutherford model. And Rutherford did an experiment where he had a very thin sheet of gold and he fired positively charged particles at the gold sheet. And many of them just passed through. Some of them got deflected at large angles, but most of them just passed through. So he postulated the theory that the atom is mostly empty space. Okay, and so he had electrons orbiting around. So he developed this model where he had electrons orbiting around a nucleus. And then, of course, the nucleus is positively charged because of protons and neutrons, and electrons are orbiting. And Niels Bohr then postulated the theory that electrons are not free to just move about because they are at discrete energy levels. So the orbits around the atom are fixed. Okay, the orbits around the atoms are fixed. And the electrons are moving in that fixed orbit. And depending on, of course, the atomic structure of each element, you have a specific number of electrons in the outermost orbits, right? And that orbit is typically known as the valence orbit, and the electrons in there are known as the valence electrons. And I assume you would have studied all of this previously in physics and chemistry, right? So the way it pertains to us is, depending on the material, these electrons have certain energy, right? These electrons have certain energy. Now, typically, without going too much into detail, the larger the orbit, the more energy the electrons have in that orbit. Okay, the smaller the orbit, the lower the energy. Every time an electron wants to move up, it acquires more energy and it moves up, right? From lower orbit to a higher orbit. When it goes down, it must release that energy. That energy is typically released in the form of heat or light. Okay, again, semiconductor physics. So all orbits have specific or specified energy, specific energy levels, and electrons can move and jump orbits. So again, electrons go up a orbit, then it acquires energy, or it acquires energy and goes up. And if it falls down, then it loses energy in the form of heat or light. Lower energy level. In larger orbits, higher. And of course, this right here Now, this right here shows you a element which has 5 electrons. So it's just a random image. It's a random image, specific element, but it's 5 electrons. When we talk about silicon and germanium and column 4 compounds in general, you have 4 electrons in the valence shell or the outermost orbit. Let's see, valence orbit. Okay, so silicon has 4 in its outermost orbit. So far, so good, right? And then silicon as a material is the second most abundant material on this planet, but it's not in pure silicon form. Okay, typically it's in form of silicates, dust, sand, right? That's where it comes from. In fact, that's how story goes that humankind invented glass when someone had a fire on a beach, and it burned all night long. In the morning, someone discovered glass. That is, the sand silicate had turned into silicon oxide, silicon dioxide to be precise. Anyway, so the silicon atom has silicon atom has 4 electrons in the outermost orbit. When you arrange these atoms in a silicon crystal, they bond with its nearest neighbors. Each silicon atom shares its 4 electrons with its 4 nearest neighbors, 1 electron each. And the neighboring atom also shares 1 of its electrons. Thus, they form a stable covalent bond, which has 8 electrons shared amongst them. Okay, so in a single crystal of silicon, you have what is known as a covalent bond between a silicon atom and its 4 neighboring atoms. Okay, so it creates a bond where you have an atom sharing, and I have this on the next page also. I'm just going to draw a close-up right here. Okay, so each silicon atom is sharing 1 electron each with 4 neighboring atoms, and thus all of them have 8 electrons in their outermost orbit. Now, the sharing of electrons creates a bond. That bond is known as a covalent bond. A covalent bond. When they're ordered in segments, they form what is known as a silicon lattice unit cell. Okay, so this illustration here shows you a unit cell. And if you look at, let's say, we look at these right here, it's hard to visualize this because this is a 2-dimensional representation of a 3-dimensional structure. But there is also a bond right here between these atoms. It forms a diamond shape. Okay, it forms a diamond shape. And so the silicon lattice structure is also known as a diamond lattice. To be clear, this has nothing to do with the diamond, the material diamond. Okay, it's just the shape of the silicon unit cell. Okay, and this of course shows an even closer view of one of the corners where 1 silicon atom is connected to 4 neighboring atoms. Now, I use the term single crystal, right? I use the term crystal. So what it means is when you have a silicon lattice and it creates bonds with the neighbors, They're ordered in periodic segments. If the structure is ordered and repeated throughout the structure, then it is known as a crystalline material. This is very important for semiconductor materials because it allows us to create or manufacture devices at random. Okay, we are able to predict the properties of the material because of its crystalline nature, meaning a silicon unit cell, diamond lattice cell, is repeated throughout that material. There is no break in the structure. It has a periodicity and it has the same material properties throughout the entire structure. There is no break in the formation. Okay, hence it's known as a crystalline material. It is also referred to as a single crystal material. A single crystal material. So crystalline structure is also referred to as a single crystal material. So might look something like this. Let's just draw it out this way. It's a random structure, and you have these bonds. It's repeated throughout the entire structure. Anyway, so there's no break, and the structure is repeated. Crystal, that's called a single crystal or crystalline material. Polycrystalline material is basically a structure that has multiple crystalline structures inside. Multiple crystalline structures. Meaning there are crystalline portions in the material. They are ordered in segments, but they are not repeated throughout the material, hence polycrystalline. So an example would be something like this. You would have a random space where you have crystalline material. As I said, completely random. Okay, so crystalline within, but not extending throughout the entire piece of the material. And then amorphous has no ordered structure. No ordered structure. And this is not applicable only to silicon, it's applicable to any material. Okay, you have crystalline solids, semi-crystalline, which is polycrystalline, and then amorphous. I actually had some silicon wafers in my office. I wanted to bring it for sure until I forgot, so I'll bring them on Friday. Okay. Any questions so far? All good. All right, from here, we'll go into energy band structure. So we talked about how silicon atoms form a covalent bond with your nearest neighbors, right? There's also something known as ionic bond that happens in compound semiconductors. Okay, that's a little bit of a tangent. So for instance, let's say we make gallium arsenide. Gallium arsenide is from 3 and 5, right? Column 3 and 5. Let's go back to that slide. 3 and 5, or 2 and 6 for that matter. So if it's 3 and 5, in silicon, you have 4 electrons and 4 electrons in the neighboring atom, right? So they're equally shared. So there's equal attraction or equal pull on the electrons from the neighboring nuclei. Okay, 4 electrons, 4 negative charges, 4 positive charges. So equal attraction on all sides. In a 3-5 compound semiconductor, there is unequal attraction. Okay, unequal attraction. Column 5 has 5 electrons, right? So if it has 5 electrons, 1 more electron than the nucleus neighboring, which is in the gallium. And so there's a slightly more pull towards the arsenic side versus the gallium side. And so all those forces that are acting inside the atom, they hold that structure together. Okay, they hold the structure together. In a covalent model like silicon germanium, the covalent forces, the covalent bonding holds the structure together. In a compound semiconductor, that force is that bonding is known as an ionic bonding. Okay, ionic bonding. So I'll note it down here. And ionic bonding is in compound semiconductors. Okay. Okay. So each one of these electrons that is orbiting in the outermost shell has certain energy. When you bring them close together with other atoms, the electrons from neighboring atoms are not shared, right? So the outermost orbit has electrons from 1, 2, 3, 4, 5, right? Because 1 electron each is shared with 1 neighboring atom. So you have 5 atoms that are sharing those electrons. So instead of 1 single energy level, now there is an energy band in that outermost orbit, right? You had an atom that was shared here and here, here and here, here and here, here and here. And 4 neighboring atoms. So there are at least 5 energy levels to speak of. Make sense? And that creates energy bands, which leads us into an energy band diagram. Have you encountered this before? Energy band diagrams? Okay. So let's start on the far right. Yeah, let's start on the far right. We have electrons in the valence band, right? And then what we have is the conduction band, where the electrons are free to move around. Okay. So as I said, there's discrete energy levels in the valence band. And in the valence band electrons, if there's enough energy that they're completely free to move about, then without the application of any external energy, the conduction bands and the valence bands overlap. And we have what is known as a conductor. So in conductors, materials that are conductors, the valence band and the conduction band overlap. There's always free electrons available to move around the material, which allows us to conduct electricity. Okay. And this energy band diagram, the arrows pointing up is basically the energy states or the energy levels. Okay, energy levels moving up. Again, it's not related to this diagram specifically. There is no physical structure. Okay, it's simply an illustration of the energy levels in the atom. Then in the far left, the conduction bands and the valence bands are far apart. They are very far apart. Okay, the valence electrons are very far away from the conduction band. So the energy levels are very low. And there's a gap between the two, known as the forbidden gap or the forbidden band. Okay. So as I was saying, they all form some sort of energy band. So these are known as bands: valence bands, conduction bands, and this one is known as a forbidden band or a forbidden gap. The gap is so large that the electrons can never be excited from the valence shell, from the valence orbit into the conduction band. Okay, and that's how we have insulators. Okay, insulators. To be sure, of course, in real life, there is never a perfect insulator, right? There's never a perfect insulator. So it's never 100% insulating material. It's always some tiny element, sorry, not element, energy here and there that could allow it to cross over. But for all intents and purposes, there's never enough electrons to conduct any sort of electricity. Okay, so we have insulators on one side. We have conductors on one side, we have insulators on the other side. In conductors, the valence band and the conduction band energy levels completely overlap. So there's always free electrons available to move around the material, which allows us to conduct electricity with ease. In an insulator, there's a big gap between the two bands. Electrons cannot jump over or cross over the two bands, and hence insulating material. There's never sufficient electrons to move. Yes.
So like say a conductor, I think like a slab or a plate of like copper.
Mm-hmm.
So the conduction, it's not like a physical like layer like the Bohr model where you have valence electrons from the complete outside. It's just saying that the valence electrons are moving throughout the entire material, like just water. Essentially, that's what I'm thinking.
So the question being asked is, when we talk about motion of electrons, right? The motion of electrons, is it flowing like liquid? To be honest, not really. When we say movement of electrons, it's not the electrons that are moving a lot. Electrons will move very little. Okay, very little. When we say, okay, current is flowing, electrons are flowing through a wire, the physical movement of electrons is very small, probably like counted in microns, and then overall be like millimeters, very small. But it's the electric field that allows the charge and hence the energy to flow. That's actually moving. It's the charge that's moving. Again, definition of current is the rate of flow of charge. So that is what is transferring the electrical energy through a wire, right? So the physical movement of electrons is very minimal in real life, actually. And then, of course, when electrons move out, it leaves behind an extra positive charge. So it creates an ion or an ionic structure. But again, that we will see in the next coming slides. Any other questions? Okay. So as I was saying, we have conductors on one side, we have insulators on the other side, and in the middle, we have the semiconductors. There is a gap. There is an energy gap between the valence band and the conduction band. However, it is not as large as the insulators, and it can be overcome. It can be overcome with thermal energy, light energy, or an electric field, electrical energy. Okay. And so we have names and notations for each of these bands. The valence band energy level right here is noted as EV. Most of the electrons are right at EV. Okay, right at EV, energy level of EV, valence band energy level. The conduction band energy level is referred to as EC right here. Okay. Typically, we may have some electrons above the conduction band level, and most of the electrons will be at below the EV or the valence band energy level. And the gap between the two is noted as EG, labeled as the band gap energy. EG, of course, is EC minus EV, the difference between the two. Okay. If we look at the EG values for some of the most common ones, we see silicon is right here at 1.12. Germanium is actually even better, 0.66. But again, there are several reasons why silicon is the most preferred choice. I'll go on a bit of a tangent. Silicon has an oxide that is an excellent electrical insulator. When you oxidize silicon, it creates silicon dioxide, SiO2, and SiO2 is an excellent electrical insulator. So when you're trying to build circuits with silicon wafers, it's very easy for you to mask and create barriers between your devices by using silicon oxide. And silicon oxide, creating silicon oxide is like baking cookies. You take a silicon wafer, you stick it in an oven, and you just bake them. In this case, the baking is at 1000 degrees C. So as I said, so silicon, of course, has some disadvantages compared to germanium, but when it comes to other material properties, it has more upsides than downsides compared to germanium. Germanium also, we can create oxides, but it's not as, does not have the material properties that we would require in a semiconductor. Then we see the, let's see, there's gallium arsenide right here, gallium nitride, indium phosphide, carbon. Remember, carbon is also a column 4 compound. Depending on the structure of the carbon atoms, the the structure of the molecules, you can have graphite, or you can have diamonds. Diamond is one of the hardest known substances. Okay, when carbon is under tremendous pressure and high temperatures, you can create diamond. And that's how lab-grown diamonds are made. Chemical vapor deposition is used. You have a vacuum chamber, you pass a gas containing carbon in it, typically like methane gas, decomposes into its elements. You have carbon, and if you have a seed layer on your sample, the carbon deposits as diamond film. And you can continue depositing over a period of like 24 hours or 48 hours or 72 hours or longer. That's how it's grown. But carbon's energy gap is 5.47. And so it cannot be used as a semiconductor, right? So as I stated just a few slides earlier, just because an element has 4 electrons in its outermost orbit does not mean we can use it as a semiconductor. There's a band gap that is very large. We cannot overcome that band gap. I actually had, when I first started my doctorate, I was working with some diamond thin films. I actually have silicon wafers with diamond films on it. I just don't know in my move, it's somewhere in my office. If I find it, I'll bring it. One other point. Salt. Table salt. What compound? Sodium chloride. It's a 2,6 compound. It's a 2,6 compound. So sodium chloride crystals, but they are not semiconductors. It's an interesting fact. I need to look up what the band gap energy is for table salt. Let's see what else. So yeah, conductors, the conduction band and the valence band overlap. Insulators, the gap is far up, it's really big, far apart. We cannot overcome. In semiconductors, the gap can be overcome. Okay. In a silicon lattice, yes. Insulator band gap. right here. Yep, 5.47. Good questions. The question being asked was, what is an number example of a insulator? Carbon would be an example. Yes.
So I'm assuming semiconductors is 1 to 3 electron volts.
Approximately. Yeah, conductors, basically it's overlap, so it's like non-existent, pretty much. There will still be a number on it, but essentially I personally just refer to it as 0. So, I mean, like you can see here, like tin, I don't have like copper and aluminum and all of those metals, but essentially I just say it's like 0. But in real life, it's never completely 0. There's always some there. Okay, so remember I stated all material properties are highly dependent on temperature, right? Absolute 0 is minus 273 degrees C, right? Meaning it's so freaking cold, I can't think straight. I can't move about. You can't do anything. You're just frozen solid. And the reason this is important is because when you're at absolute 0, 0 Kelvin, right? It's noted as, it's a Kelvin scale, Lord Kelvin, 0K. The covalent bonds are all intact. All the electrons are occupying the valence shells. They're all in the valence band. The energy levels are all at the valence level. Okay, they are all below EV. Okay, as the temperature rises above absolute 0, some electrons acquire energy to break free from their bonds and rise above EV and go into EC. So they acquire enough energy to jump up a orbit, and that would be thermal energy. Okay, because it's heating up. Absolute 0, minus 273 degrees. It's heating up. Once it heats up, that's thermal energy that is acquired by the electrons to break free from their covalent bonds. So typically, all of these dots that you see here, these are all shared electrons. Okay, and each of these electrons is filling a spot in the crystal lattice. They're all below EV level. Once it heats up, it moves from this level to the EC level, from the valence band to the conduction band. And so when we get all the way up to room temperature, there are a certain number of electrons that are already freely moving around the crystal lattice. Okay, and that is what makes it an intrinsic semiconductor. Okay, so at room temperature, and room temperature is, so 0K is minus 273 degrees C. Room temperature, typically it's about 25 degrees C, but to round it up, you call it 300 Kelvin, so 27 degrees C, which is kind of hot. Well, not quite hot, but warm. So there's plenty of electrons that have acquired enough thermal energy to break free from the covalent bonds. They're now in the conduction band, so they're free to conduct. They're free to move around the crystal lattice. Not as much as a conductor, like not as much as a conductor, but enough to be called a semiconductor. Okay. So every electron, and this concept is very important, every electron that moves out of its bond, it's not part of an atom at all. Okay. So a negatively charged particle has moved out of its spot. What is left behind? A hole. It's not quite a defect, but it's a hole. It's an empty spot. And that empty spot is referred to as, you just said it, a hole. It's not a defect. It leaves behind a hole, and because the electron took its negative charge with it, the atom and that surrounding spot right there has one extra positive charge due to the nucleus. And so the hole is said to be a particle with a positive charge. So if these are the spots, these are the spots, and you have an electron here, let's say an electron jumps here, then this hole is moving here. So electron moves here, and the hole moves to the right. So every time an electron jumps over, the hole is moving in the opposite direction. Electrons move to the left, holes move to the right. Well, opposite. Yes.
The feel, right, to think about it as like the electron builds in the hole, and by doing that, it creates a new hole.
Yes, that's exactly what happens. That is exactly what happens. And yes.
Bring like physics, like where you pull this thing is like this continuous rate. That's
You're going into string theory? No, we won't go quite deep into that. There's another hand raised here. Okay. But when I said important concept is because entire analysis that we do in 306 and going forward, you'll refer to electrons and holes. Okay. So it will help. It helps. It not just helps. It's emphasized that we treat the hole as an independent particle with positive charge. Okay. Diodes and transistors will say, okay, electrons are flowing this way, and then we'll, right after that, there'll be a statement saying holes are flowing this way. I mean, opposite way. So we'll say electrons might be flowing in this direction, and then holes are flowing in the opposite direction. But again, in solid state physics and electronics analysis, we refer to a hole as an independent particle with positive charge. But the concept is that the electron moves out of a bond, leaves an empty spot behind it, and as it moves around the crystal lattice, it jumps into spots, and correspondingly, an empty spot moves in the opposite direction, and an empty spot is termed as a hole with an extra positive charge. One final thing is when an electron fills a hole, it is known as recombination. It recombines with the hole, it gets rid of the negative charge and the positive charge. And the recombination results in energy dissipation in heat or light. A heat or light. Okay. And then these electrons that are free to move about at room temperature are what creates an intrinsic semiconductor, meaning if you take a semiconductor, it has free electrons to move around, not enough as to the level of a conductor, but much higher than an insulator. And there's an equation here which describes the intrinsic carrier density. And this equation is, I believe it's also part of the homework assignment, but it's a simple plug and play equation, okay? Ni refers to the intrinsic number of electrons or carriers. Sorry, I'm going over time. If you have to leave, you can leave. This will all be recorded. This is all being recorded and will be posted, on the in the playlist. So the intrinsic carrier number is given by B T cube E raised to minus EG over KT. Let's take a look at each of these terms. B is a material dependent parameter, and it has to do with thermal conductivity and the lattice structure. Okay, thermal conductivity of the lattice structure and the mobility of the carrier electrons. And T is the absolute temperature in Kelvin that would be given as part of the problem itself. Determine the intrinsic carrier number at 300K, 400K, or the 200K. So you have B, you have T, and then you have EG levels from the table in the previous slide. right? You have the EG levels right here. Band gap. And then KT. K is the Boltzmann's constant, which is already a known number. And T again is the temperature. Okay. And that gives you the intrinsic carrier concentration. Okay. Intrinsic carrier concentration. So sorry to rush and go over time. But again, if you have any questions, feel free to reach out to me. Also, I thought it was a given, but I'd like to state you have access to the book. So anytime I cover some material in class, please read the relevant section. Okay, so I'm not assigning any reading sections, but anytime I cover a topic in class, please read that specific paragraph. It's not very long. Read through it, scan through it, and then reach out to me if you have any questions. Okay. All right, we'll end class here today and we'll pick up here on Friday.